So now we're going to talk about the types of electronic transitions that can take place within an atom and the corresponding results, whether or not photons or energy in the form of radiation would be emitted or absorbed. So let's talk about the difference between what is called the ground state and the excited state of an atom or electrons. So whenever you have an electron or electrons in their lowest possible energy levels, they're said to be in the ground state, right? And pretty much any other state would be the excited state. So any other energy level above the ground state, we call that the excited state. So basically you can have electrons being promoted from lower energy states to higher energy states. And this is normally done by some process where electrons are being absorbed, or I should say energy is being absorbed. And some examples are listed here: electrical discharge, heat, lasers in the form of photons, and so on. Then you can have the possibility of an electron being in an excited state and it can relax back to the ground state. We call that relaxation, all right? And when that happens, radiation would be emitted, all right? And it can be emitted, for example, as a particular color of light, or it may not be. It may be emitted as some other form of radiation as well, all right? So this is what happens when you have either a transition where excitation is taking place or relaxation is taking place. So what this represents here are different energy levels or orbits for an atom. This is the n equal 1 orbit, n equal 2 orbit, n equal 3 orbit, n equal 4, n equal 5. And we have an arrow here labeled A, which represents the transition from n equal 1 to n equal 5. Obviously, that means that energy for the electron would have increased when it makes that transition. So that would be an excitation process. And then you can have a situation where the electron falls from a higher orbit to a lower orbit, such as going from n equal 1 to n equal 4 to n equal 2, or n equal 4 to n equal 3, or n equal 3 to n equal 2, all right? And that represents relaxation, all right? And that's basically what happens when it comes to the electron transitions in an atom, according to the Bohr model. Now, it's very important that you understand the relationship between the value of the energy transitions and the wavelength and frequencies associated with those transitions. Now, the statement here is about the model that is being used here, and that the energy gap here is inversely proportional to the wavelength of the radiation responsible for that transition. So in other words, delta E, remember, is equal to h nu, right? Which is equal to hc over lambda, right? So basically, the larger the energy difference between the two orbits where the transition is taking place, the smaller would be the wavelength. So that's an inverse relationship between the wavelength and the energy gap between the two orbits for the transition, all right? So basically, the shorter wavelengths would correspond to higher delta E values, and the longer wavelengths would correspond to lower delta E values. All right, so we're going to stop here. The next topic we're going to discuss is the de Broglie equation, all right, and some other things as well. Okay, until next time.